Hi everyone. Today I'll be talking about this AAAI 2020 paper, Uncertainty Aware Action Advising for Deep Reinforcement Learning Agents. This paper was by Da Silva, Leal, Kartal, and Matthew E. Taylor from the University of Sao Paulo, Brazil, and Borelius AI, Canada. The goal of this paper is pretty straightforward. We have a deep reinforcement learning agent. What we want is to advise this agent. So there has been growing interest in human advisable deep reinforcement learning and advisable deep reinforcement learning in general. But one of the core problems that most of the methods suffer from, or at least have, and this is considered as a separate research problem, is when exactly do you ask for this advice? And what would be a good time to ask for such an advice? The solution this paper presents is basically the agent would want to ask for an advice when it is uncertain about taking an action. The motivation of this paper is pretty straightforward, as they also note in the abstract section. The advice is limited, it's costly, and therefore must be efficiently used. Not only that, it must also be requested only when the agent really requires it. Hence, they present this framework known as requesting confidence moderated policy advice. Basically, what they're trying to do is they are trying to come up with a confidence measure that will be used to query the humans or the other agent in the loop who is providing this advice. There are two contributions of this paper. The first is coming up with this uncertainty measure. The second is how do you incorporate this measure into popular deep reinforcement learning algorithms like DQN, which is an off-policy algorithm, and A3C, which is an on-policy algorithm. I'll talk quickly about what happens if, let's say, God were to give you an uncertainty measure. So this paper has a pretty straightforward algorithm for that. This algorithm 1, which is RMCP, provides us with the framework of what to do when we have such a measure. What basically it says is, let's say we have a Q function, right, which is being approximated by the agent, which has a policy pi, and we have this ideal uncertainty estimator mu, right, and we also have the advising agent, which has the policy pi delta. Now what this RCMP algorithm says is basically you initialize your Q and pi as usual, and within each learning step you observe S as usual, and then you calculate this uncertainty measure based on this S. If the uncertainty measure is high enough, then you ask for the advice. If not, then you just get the action using the normal policy, and finally you apply this action A, which you have gotten either from the advisor or from your normal policy, and observe the next state and the reward S prime and R respectively, and then finally you can update your Q values and pi with this tuple SAS prime R. The thing to note here is that this mu function is a function of the current state S. Before moving on, we can start with an existing work and try to see what basically are we trying to achieve here. One of the very influential works in this whole category of human advising or advising in general has been this notion of importance advising by Torrey and Taylor in 2013. The notion of importance advising is basically if there is a demonstrator or an advisor who has their own policy, right? They have their own policy in their head, which they'll probably advise. Now let's also assume the presence of Q values in their head. So not only do they know the best action, but they also know a notion of magnitude in their head. Like this is the margin, how action A1 is better than A2. In fact, their assumption is much stronger than this argument. So what they basically assume is the presence of the Q function in the advisor's head. So the advisor basically knows this QSA. Now the answer to this when to ask for advice question is pretty straightforward. They say at any state, if the max and min Q value in the head of the advisor crosses a certain threshold, then we'll just provide the advice. The critical difference here is the presence or the assumption of the presence of such a Q function in the advisor's mind. Typically, in the original work, they really assumed an RL agent is trying to advise another RL agent. In this case, this assumption makes sense because, well, RL agent, if it's a Q learning based agent, it has some Q values, right? At least as long as it's not policy gradient based, it most likely would have some Q value, and then you can just provide this Q value information to your current agent, and this agent can then use those things to be smart about when to request, or this agent can be smart about when to provide an advice. But here the setting is slightly different. Here what we want is the agent, which is acting in the world, should be able to figure out on its own whether it is uncertain or not. This is known as epistemic uncertainty, which is basically knowledge about the uncertainty about a certain fact. There are two kinds of uncertainties in theory. The two are aleatoric and epistemic. The first basically means that there is some inherent uncertainty that lies in the system itself. It can never be reduced, regardless of how much knowledge you gain about the system. The second is epistemic uncertainty, which is the uncertainty that I have because of the lack of knowledge. Now, it can be reduced if I were to gain more knowledge by either interacting or getting some extra information about the world. So here what authors are trying to do is reduce or at least measure this epistemic uncertainty and then use a threshold on this uncertainty to determine whether the agent should request an advice or not. Now the theory could be very broad, but the work itself is pretty straightforward. What they want to do is, let's say we have a function approximator that can predict or evaluate some Q values for the current state action pair. So let's say this is a function approximator that spews out this QSA. You give it a state, you give it an action, and it will tell you the Q value. This work basically resort to something known as some form of ensemble methods. So instead of having one such approximator, what one can do is have multiple such approximators. Now asymptotically, all of these Q values should be the same, right? Because if all of these approximators are correct and they have all converged, all of these Q values should be the same. There is no difference between any of these Q values. But this doesn't happen as the learning begins, right? So at the beginning of this learning phase, all the Q values are not the same, because all of these approximators may be learning different things while they are interacting with the world, maybe because they have been trained with different batches of experiences, or there could be tons of other reasons, right? Exploration is one of them, or maybe the biggest one of them. The key insight here is that if for a certain state and action pair, all of these Q values disagree by a significant margin, then we can construe that there is some form of uncertainty. This is similar to importance sampling, right? Because in importance sampling, the uncertainty measure was in fact Q max minus Q min. Here, what the authors say is, instead of doing this max minus min business, what we can do is we can have multiple Q value approximations, and then we can take the variance of these Q values. So what we'll do is compute the variance across these Q values and then normalize it, which is our mu function now. And then if this variance is greater than some threshold, then we say, oh, we are uncertain, and then we being the agent needs to request for advice from the humans. There are a couple of questions that people can ask. For example, well, it would require tons of more parameters. That is true, and in some way you can reduce it by splitting the whole approximator into two sections. The first section would be about feature extraction, and the second would be about Q value prediction. Now, if this is the case, which is typically the case for image based at least, or in fact a lot of machine learning neural network based approximations have this kind of paradigm where couple of layers try to extract feature, and then couple of layers try to perform some value prediction or classification. Now, if that's the case, which is usually the case, then what you can do is all of these Q values can share the same function feature extraction method. If that is the case, then you have at least saved all of these weights, right? You don't need to train them again and again. And this paradigm is known as creating multiple heads, because these can be seen as different heads for the same approximation strategy, and the variance across heads is used as the uncertainty measure. Finally, if all you need is multiple heads, then how do you train a conventional algorithm, deep learning algorithm like DQN or A3C, which are fundamentally different? Like one is off policy, which is DQN, and another is on policy, which is A3C. The authors here say, well, it doesn't really matter, right? If they're on policy, off policy, blah, blah, blah. What really matters is if they are predicting the Q values or not. And in fact, both of these methods, well, Q value based DQN method depends on Q values. A3C is an actor critic based method where the actor is for computing the policy or predicting the policy, and the critic is for computing the value or the value function, or in some cases Q value function. The second contribution of this paper is, okay, we have this uncertainty measure which requires multiple heads. How do you incorporate it for an algorithm? A general sketch of this I can tell in the DQN paradigm is, okay, we have all of these Q values which are coming out of different heads, and there is a function, there is a feature approximator, and then there are multiple heads which all give out different Q values or same Q values depending upon the learning stage. What we'll do is we'll train all of these via separate losses. So each of these will have a separate loss function, right? And then all of these would be trained separately, given by here, where each Li is the loss function for the ith head, and this is basically the TD error for DQN. Similarly, this is the case for A3C, where all the heads have a separate loss function. Now, this is pretty straightforward to implement in any of the algorithms that try to predict Q value, and I must say that there are many algorithms that do that, including a huge number of actor critic methods and a huge number of DQN variations that are out there. So this is an example of the multi-head approach that these guys are proposing, where you have your inputs and hidden layers, and instead of predicting one QSA, you predict multiple such QSAs, and the uncertainty amongst these is computed by the variance amongst these Q values. Now they perform experiments using two domains, the grid world domain and the Pong domain. It is expected, and they also show empirically, that initially this variance was pretty high, and as you progress in the learning phase, this variance is supposed to go down. The important factors here is how many heads do you use, right? That's an interesting question. And the second is, what is this threshold? My comment to this paper is, well, they do provide some insights, which is this ablation kind of thing, where they try out different heads and they empirically show, okay, using more heads reduces some form of noise that may occur, and it's better maybe in certain cases. Well, there's no conclusion, but at least there is some discussion, right? But for the second question, right, what is this threshold that we can use on this uncertainty measure? I don't think that has any discussion, right? Although it's an important thing, but sadly that doesn't have a discussion. Now, one could argue that, okay, a lot of machine learning algorithms have a lot of hyperparameters, and not always do you have great insights onto each of them. But I think since it is very critical for this algorithm to even function, right? There should have been some studies or some insights that the authors would have based on their experiments or their thought processes that they would want to include in this paper, and I would have really appreciated if that would have been the case. Finally, the results are pretty straightforward, that the expectation is that this method, which is the RCMP method, is a better active learning strategy, and they compare using 4 algorithms: their own, the random, where you just randomly seek advice, no advice, and finally using importance advising. It is well known, and they also establish using their experiments, that no advice is almost always worse than using some form of advice, even if the advice is not that helpful. Finally, some interesting lines of thought that this paper gives is, how would the demonstrator be, right? Would they be able to provide advice at all points? The answer is no, and they take account of this. And what happens if they are not the best advisors, right? If they're making some form of mistakes. So to summarize, the bigger idea of this paper was, we'll come up with an uncertainty measure to actively query a certain demonstrator, which could be a human, which could be another RL agent. And the whole motive here is to reduce the number of queries we can do. Their strategy is that if the agent has a lot of estimations of the Q value for the current state and action, then the variance in that could be used as that uncertainty measure, and a threshold over that measure could then be used to further operationalize whether or not to query the advisor in the loop. So this was uncertainty aware action advising for deep RL agents. I hope you liked my explanation, and I'll see you guys in the next video.